Okay, so welcome back to this next video in which we are discussing the PI3 kinase AKT mTOR pathway. Okay, so in the previous video what we saw is the activation of receptor tyrosine kinases, which are now going to activate the PI3 kinase AKT mTOR pathway. Okay, right, so let's start with what PI3 kinase is. So PI3 kinase is often abbreviated to PI3K, okay, and this is often spoken PI3 kinase. Now, its full name is then phosphainositide 3 kinase. So the PI stands for phospho, and then the I is for inositide, and then it's phosphainositide 3 kinase. Now, there is not actually just one phosphainositide 3 kinase, it's actually an entire family of enzymes, okay? Now, to talk any more about the different types of phosphainositide 3 kinases, we really need to know something about what a phosphainositide is. So that's going to be my first topic. I'm going to tell you all about phosphainositides, okay? Now, to discuss phosphainositides, we need to know what phosphatidyl inositol is. And in order to know what phosphatidyl inositol is, we need to know what phosphoglycerolipids are. And in order to know what phosphoglycerolipids are, we need to know what phospholipids are. And then to talk about phospholipids, we need to talk about lipids. So then, I'm going to start off by discussing what a lipid molecule is. Okay, so a lipid molecule then. A lipid molecule is the scientific name for a fat molecule. Okay, now what actual characteristic does a molecule have to have in order to be considered a fat molecule? Okay, well it needs to be extremely neutral. Okay, so it needs to have an extremely neutral structure. The bonds in it need to be non-polar. Now, this means then that these structures, these lipid molecules, do not interact well at all with water, and they become hydrophobic. So let me just remind you of water's polarity. Okay, so if we have a water molecule here, a H2O, so an oxygen linked by two covalent bonds to two hydrogen atoms. Okay, each of these covalent bonds between the oxygen atom and the hydrogen atom is a single covalent bond, and therefore has two electrons in, one from the oxygen and one from the hydrogen. Okay, so let's just colour this in. So let's say that this one comes from the hydrogen in red here, okay, and this one here comes from the oxygen in blue here. Okay, right. Now, the next question that arises is, are these electrons that are in this covalent bond, are they sitting directly in between the oxygen atom and the hydrogen atom, or are they tilted to one side? Okay, and in order to answer that question, we need to think about what forces are going to be on these electrons. Okay, well, these electrons are going to be feeling attraction to both the nucleus of the oxygen atom and the nucleus of the hydrogen atom, because remember, nuclei consist of neutrons and protons. Neutrons are neutral, and then protons are positively charged, so nuclei are overall positively charged. Electrons are negatively charged, so they're going to feel an attraction towards the positive charge of the hydrogen nucleus and the positive charge of the oxygen nucleus. We need to assess which of those attractions is stronger. Now, you might say, well, surely it's the oxygen, because the oxygen is going to have multiple protons within its nucleus, whereas the hydrogen only has one proton. So surely that will mean that the oxygen pulls much harder. But then you also have to factor in the fact that hydrogen has no electrons that are surrounding its nucleus other than these two electrons here that are in this covalent bond. Okay, so there's nothing shielding the positive charge of this proton from these electrons, whereas in the case of oxygen you have loads of other electrons around it which are shielding it from the electrons, basically, or rather shielding the electrons from the positive charge. Okay, right. So when you take into all of these, into consideration all of these facts, overall oxygen pulls on these electrons harder than hydrogen, so these electrons end up tilted towards the oxygen. Okay, now there's a fancy word for how strongly an atom pulls on the electrons within a covalent bond, and this is electronegativity. So we say that oxygen's electronegativity is greater than hydrogen's electronegativity, and what this means is that oxygen atoms pull on electrons in a covalent bond like this harder than hydrogen atoms. Okay, so the electrons end up tilted towards the oxygen atom, and that's for both of these bonds. Okay, now that gives the oxygen atom a slight negative charge, a partial negative charge here, written delta, which means partial negative charge. Okay, whereas these hydrogen atoms here, these have lost the electrons are further away from them than they should be, and therefore they get partial positive charges. Okay, so this is what is meant by water having a polar structure. Okay, you have these partial negative and partial positive charges. Okay, so this side of the water molecule is negative, this side rather is positive. Okay, now this means that two water molecules can actually interact with each other really well. Okay, so if we put another water molecule here, okay, this one too will have the partial negative charge over here and the partial positive charges over here. Okay, so let's colour those in. So these hydrogens are both partially positively charged, and the oxygen is then partially negatively charged. Okay, now the oxygen, firstly, the partial positive charge on this hydrogen here can now interact nicely with the partial negative charge on this oxygen here. In addition, you have to also consider the fact that oxygen actually has two lone pairs of electrons here and here. Okay, so in addition to the two bonds that it's got to hydrogen atoms, it also has these two lone pairs here. So these are lone pairs of electrons. Okay, and what can happen is this hydrogen here, which is partially positively charged, not only is it going to interact with the partial negative charge of the oxygen, but this is also a centre of negative charge. You've got this little site where you have two electrons sitting, and these are a centre of negative charge. So this partially positively charged hydrogen is going to interact with that lone pair of electrons, basically. And this forms quite a strong form of intermolecular bonding. Okay, and this form of intermolecular bonding is known as a hydrogen bond. Okay, and these are quite strong. So, water molecules can interact with each other very, very well. Now, if we take a neutral molecule, which means a molecule which has a highly neutral structure, okay, so all of the electrons in its covalent bonds will be in between the two atoms perfectly, so there's no charge, everything's just neutral, then will water molecule be able to interact very well with that neutral molecule? Well, the answer is no, okay, and the reason is that the bonds that it can form are going to be much, much weaker than these bonds that you have between two water molecules. So, if you take a fat molecule and dump it in water, if you try and mix loads of fat molecules, let's say, with water, what ends up happening is that the two layers separate. Okay, the fat and the water will separate, and the reason is that they're trying to make the contact between the water and the fat molecules as small as possible. Okay, so basically fatty molecules do not interact well with water, and this is the reason that fat molecules tend to aggregate together when you dissolve them in water. It's not that the fat molecules interact well with each other, it's that they all interact terribly with water molecules, and the water molecules all want to interact with other water molecules, and they end up aggregating all of the fat molecules to one side. So basically they shove the fat molecules to one side. So if we have our container here, you've got fat on one side and water on the other side, basically. And that's the way that they can reduce the interaction between water molecules and fat molecules as much as possible, basically. So fat molecules tend to all end up aggregated together, but it's not that the fat molecules do not all interact well with each other, it's that they all interact terribly with water molecules. So the water molecules all shove them to one corner, basically, so that they can interact nicely with other water molecules whilst the fat molecules are out of the way, basically. Okay, so let me give you an example of a fat molecule, the sort of archetypal example of a fat molecule. So a whole category of fat molecules are what are known as long-chain carboxylic acids. Okay, now long-chain carboxylic acids, as the name suggests, are carboxylic acid molecules which have a really, really long tail. Okay, they're also actually called fatty acids, and fatty acids is kind of the old name for long-chain carboxylic acids. Okay, so they're not the only type of lipid molecules. There are other types of lipid molecule, but this is a major category of lipid molecules, and they're often used to build other types of lipid molecules as well. Okay, as we'll see. So, let me give you the sort of archetypal example then of a long-chain carboxylic acid. So the archetypal example is then stearic acid. And stearic acid is the old name for a molecule that would now be called octadecanoic acid. Okay, and although octadecanoic acid is more of a mouthful than stearic acid, it's a more useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with an 18-carbon, fully saturated carboxylic acid. That's what octadecanoic means. 18-carbon, fully saturated carboxylic acid. So here we have our carboxylic acid group here. Okay, now we're going to need 17 more carbons, okay, because this counts as the first one. To take us up to 18, we therefore need 17 more. This means that we're going to have 16 of these in the form of methylene groups, which is just a carbon with 2 hydrogens coming off. Okay, now because I don't want to have to draw out 16 methylene groups, what I'm going to do is bracket this one methylene group that I've drawn here, and then put a 16 at the subscript there. Okay, that's a useful trick for getting around having to draw 16 methylene groups. Okay, this means repeat this structure that I've got here 16 times. Okay, that takes us up now to 17 carbons. The final one then is just going to be a methyl group on the end here. Okay, so this then is the structure of octadecanoic acid, an 18-carbon, fully saturated carboxylic acid. Now you'll see that this tail that we've got here is an extremely neutral structure, and the reason that it's extremely neutral is that it consists of only bonds between 2 carbon atoms, firstly. Okay, now these are not going to be polar, okay, because the electronegativity of both of these carbon atoms is going to be the same. So the electrons are going to feel the same pull towards this carbon as they do towards this carbon, and are therefore going to sit in the middle, basically, which means that the whole bond is going to be neutral. Okay. In addition, we've then got carbon and hydrogen. Okay. Now the electronegativities of carbon and hydrogen are roughly the same. So the degree to which carbon pulls on electrons is roughly equal to how much hydrogen pulls on electrons. So again, the electrons in this single covalent bond between a carbon and a hydrogen atom will, roughly speaking, be in the center. Okay, so all of these bonds are non-polar, so this is an extremely neutral structure. So it doesn't interact well with water and is therefore hydrophobic, and therefore we consider it a lipid molecule. It will aggregate with other hydrophobic molecules, not because it interacts well with them, but because it's being pushed aside by the water molecules, which all want to interact with other water molecules, and that's why all the lipid molecules get pushed together, basically. Okay, right, so that concludes our discussion of the lipids. Let's now go on to phospholipids. Okay, so we're gradually progressing our way towards phosphoinositides. Okay, so what then is a phospholipid? So a phospholipid is a molecule which contains, well, it needs to satisfy 2 criteria. If you've got a molecule and you want to check whether it's a phospholipid, you need to check that it satisfies 2 criteria. Okay, so the first criteria is that it must contain at least 1 long-chain carboxylic acid within its structure. Okay, so it needs to have one structure similar to stearic acid, and I want to stress that there are many other long-chain carboxylic acids other than stearic acid. Okay, so there's absolutely loads of them. All you have to have is a really long hydrophobic tail. Okay, so you need to have at least one long-chain carboxylic acid within your structure. That's the lipid component. That gives you your name as a lipid. Okay, the right to call yourself a lipid. And then the phospho component is that you also need to have a phosphate group within your structure. So let me remind you of the structure of a phosphate group. So remember, a phosphate group consisted of a phosphorus atom, double bound to an oxygen atom, then two alcohol groups coming off the phosphorus atom, and then a single bond to an oxygen atom, which has then acquired an electron via ionic means and therefore has a negative charge. So, in order to be considered a phospholipid, you have to have at least one long-chain carboxylic acid within your structure, and you also have to have a phosphate group within your structure. Those are the only two criteria that you have to obey in order to be a phospholipid. Now, we are going to now look at phosphoglycerolipids, which are a large category of molecules which are all considered phospholipids. So they are all phospholipids because they obey these two criteria here. Now I want to stress that they are not the only family of phospholipids. There are other molecules that are found within cells which are considered phospholipids, which obey these two criteria, which are not phosphoglycerolipids. But it's likely that when you think of a phospholipid in your head, what you will be thinking of is in fact a phosphoglycerolipid. Okay, so these are all phospholipids, but they are not the only phospholipids. Okay, so let's now discuss phosphoglycerolipids. So all phosphoglycerolipids are based upon the structure of one molecule. Okay, a type of molecule. It's not one molecule, as we'll see. Okay, they're based on a molecule known as phosphatidic acid. Okay, so I want to now discuss what phosphatidic acid is, because it's the core phosphoglycerolipid. It is a phosphoglycerolipid, but it's the core one. All the other phosphoglycerolipids are derived from phosphatidic acid. So we need to start with phosphatidic acid, then we'll discuss how you convert it into a more general phosphoglycerolipid, and then we'll discuss a specific example of a phosphoglycerolipid, which is phosphatidylinositol. Okay, so phosphatidic acid then. Phosphatidic acid is the core phosphoglycerolipid. Now, phosphoglycerolipids, what does their name suggest? They're going to have phospho. Okay, so they're going to have a phosphate group within their structure. They have the lipid bit here. That most likely means that they're going to contain long-chain carboxylic acids. And the glycero in the middle implies that they contain glycerol, and that's spot on, basically. Okay, so phosphatidic acid then consists of a glycerol molecule here, which will be represented by this vertical green line here. Okay, so this is going to represent glycerol. Now, glycerol, once again, is an old name for a molecule that would now be called propane 1,2,3-triol. Okay, and although propane 1,2,3-triol is definitely more of a mouthful than glycerol, it's a more useful name, once again, because it tells us exactly what we're dealing with. It tells us that we're dealing with a 3-carbon molecule, propane, where you have alcohol groups coming off the first, the second, and the third carbons. Okay, now, to the alcohol group that comes off the first carbon, we are going to attach a long-chain carboxylic acid. We're also going to do this for the second carbon. Okay, so these horizontal lines, which I'm now going to colour in green here, these are going to represent long-chain carboxylic acids. And for short, I will abbreviate these to fatty acids, and I'll abbreviate that to FAs. Okay, for fatty acids. So we are attaching two long-chain carboxylic acids to the alcohol group that comes off the we're attaching a long-chain carboxylic acid to the alcohol group that comes off the first carbon of the glycerol molecule, and also a long-chain carboxylic acid to the alcohol group that comes off the second carbon of the glycerol molecule. Okay, and this attachment is going to be done via an esterification reaction. So let me show you how an esterification reaction occurs. So here, let's let this represent our long chain carboxylic acid. So this R here means an arbitrary group there, and we'll imagine that it's a very long tail basically. Okay, we've then got the alcohol group that comes off our glycerol molecule here. So I'll colour this in green here. And now what we want to do is attach our long chain carboxylic acid to the alcohol group via an ester link. Okay, so what's going to happen is the alcohol group is going to come off the carboxylic acid group. The hydrogen is going to come off the oxygen of the alcohol group. You're going to combine these two things together to make water, and you're then going to bind the carbon of the long chain carboxylic acid to the oxygen of the alcohol group, and this then is going to be the ester link. Okay, and of course the byproduct that it will produce is water here. So once again, it's a condensation reaction. Okay, so that's how we're going to attach these two long chain carboxylic acids to the alcohol groups that come off the first and second carbons of the glycerol molecules. Okay, right. Now that's not phosphatidic acid complete yet. We haven't got the phosphate. Okay, so we're going to now attach a phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule. Okay, so we're going to put a phosphate group here. Okay, now this is going to be attached on once again via phosphoester link. So let me just remind you of how phosphoester links work. So once again, if this is the alcohol group that comes off the third carbon of the glycerol molecule, then we're going to bring in our phosphate group here. Okay, which remember consists of a phosphorus atom double bound to an oxygen atom with two alcohol groups coming off either side, and then a single bond to another oxygen which has acquired an electron via ionic means and therefore has a negative charge. Okay, to combine these together then, what you're going to do is take the alcohol group off the phosphate group, you're going to take the hydrogen off the oxygen of the alcohol group. Okay, you'll combine those two again together to make water, and you're then going to bind the oxygen of the alcohol group to the phosphorus atom of the phosphate group, and once again this bond here is called a phosphoester link. Okay, right, so this is how we're going to attach a phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule. And this structure that we've now got here is phosphatidic acid. So you've got a glycerol molecule, and off the first and the second carbon's alcohol groups, you've attached long chain carboxylic acids, and off the third carbon's alcohol group, you've attached a phosphate group via phosphoester link. Okay, so this is phosphatidic acid. Now the first thing to say is that there is not just one phosphatidic acid molecule, there are multiple phosphatidic acid molecules. Okay, and the reason for that is that I did not specify what these long chain carboxylic acids in position 1 and position 2 should be. In fact, those can be anything you like basically. There are many different long chain carboxylic acids that you could have here and here. Okay, so that means that there are many different phosphatidic acid molecules that you can make. The second thing I want to talk about is what the difference between phosphatidic acid and phosphatidate is. Okay, so people will often talk a lot more about phosphatidate than phosphatidic acid. Okay, and the reason is that in cells you have a lot more phosphatidate than you do phosphatidic acid. Okay, so let me explain what the difference between phosphatidic acid and phosphatidate is. Okay, so phosphatidic acid is actually an acid. Okay, hence its name. Now, the reason for this is that even once you've attached this phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule, you still have this group that I'm now circling in blue intact. Okay, and this is one of these carboxylic acid-like groups that I stressed earlier. Okay, now, basically what can happen is this alcohol group here can donate its proton away. So let's talk about this a little bit more. Here is this alcohol group. Okay, this consists, well, this bond between the oxygen and the hydrogen is a single covalent bond which has two electrons in, one from the hydrogen and one from the oxygen. Okay, what can happen is that the hydrogen atom can fall off the oxygen atom and it can leave its electron behind with the oxygen atom. Now, when the hydrogen atom falls off, what actually does that consist of? Because usually a hydrogen atom just consists of a proton at the nucleus and then a single electron orbiting around that. Okay, so here is the electron in red, and then we usually just have a single proton at the nucleus, which is this green particle here. Okay, so that's the normal isotope of hydrogen, where you just have a single proton at the center with an electron orbiting around. Now, there are other isotopes of hydrogen where you have neutrons as well. Okay, this is the main isotope of hydrogen. This is protium, where you have absolutely no neutrons and just a single proton with a single electron. This is the main form that we have. Okay, so it's likely that when this hydrogen falls off here, all that's going to be falling off is a proton. Okay, so we're going to be donating a proton into solution. Now, that's the definition of an acid. An acid is a molecule which is capable of donating a proton away into solution. So this molecule that I've described here is an acid because it can donate that proton off it into solution. Okay, now, phosphatidate is what's known as the conjugate base of phosphatidic acid. Okay, so once phosphatidic acid has actually donated its proton away into solution, what's left, the molecule that you have left over, is not called phosphatidic acid anymore, it's called phosphatidate. So when you have a negative charge left on that oxygen, okay, so imagine we have no hydrogen anymore, and we have a negative charge on this oxygen, that molecule is now called phosphatidate. Okay, and it's no longer an acid molecule, because what was the definition of an acid molecule? It needed to be able to donate protons away into solution. The phosphatidate molecule has a negative charge on this oxygen and a negative charge on this oxygen. It's got nowhere to donate a proton from anymore, so it cannot donate a proton away into solution, so it's no longer an acid. Okay, in fact, it's actually become a base, because the negative charge on this oxygen here is actually capable of accepting a proton out of solution, and that's the definition of a base, a molecule which is capable of accepting a proton out of solution. Okay, so that's the difference between phosphatidic acid and phosphatidate. It's this proton here. When you've got it protonated, that's phosphatidic acid. When it's not protonated, that's phosphatidate. Okay, and this is a running theme for acid molecules, that you start off with an acid molecule which is protonated. When it donates its proton away, it becomes a conjugate base. Okay, it gains a negative charge. It's no longer an acid because it can't donate another proton away. It is now in fact a base because it can accept a proton onto that negative charge, and it's called the conjugate base of the acid molecule. Okay, right, so that's the difference between phosphatidic acid and phosphatidate. Now, phosphatidic acid molecules are less present within the cell than phosphatidate molecules, because under physiological pH, which is around 7.45, most phosphatidic acid molecules have donated their protons away and therefore are existing in this phosphatidate form. Okay, and you do have some phosphatidic acid molecules and phosphatidate molecules within the cell. Okay, so they are a component of the phospholipid bilayer. Okay, so phosphatidic acid molecules are all phosphoglycerolipids. Okay, so they are, if you like, the core phosphoglycerolipids. All the other phosphoglycerolipids are going to be derived from them. Now, let's also just check that they satisfy the condition to be a phospholipid. Okay, well, to be a phospholipid, they had to contain a long-chain carboxylic acid. We've done that twice, in fact, so that's fine. And they had to have a phosphate group, which indeed they do have. So all of these molecules are phospholipids. Okay, now, all the other phosphoglycerolipids are going to contain phosphatidic acid within them. Okay, so they are all going to be phosphoglycerolipids and phospholipids as well. Okay, so how do we build a more general phosphoglycerolipid from our phosphatidic acid? Well, basically, we use this existing group that I've highlighted in blue here. Okay, we know that this carboxylic acid-like group can interact with alcohol groups in a way similar to carboxylic acids. So what if I was to bring along a molecule which contains an alcohol group? Okay, this could bind to this carboxylic acid-like group within the phosphate group of the phosphatidic acid molecule via a phosphoester link. So what could happen is we could take the alcohol group off the phosphate group, we could take the hydrogen off the alcohol group, we can combine those two together to make water, and then we can link this phosphorus atom of the phosphate group to the oxygen atom of that alcohol molecule, and this is how we make more general phosphoglycerolipids. We stick an alcohol group containing molecule off the phosphate group of the phosphatidic acid molecule, okay, and that's how you create a more general phosphoglycerolipid. So there are a huge number of different alcohol group containing molecules that you can add on here. In the next video we'll discuss myoinositol, which is the one that's going to be added on to create phosphatidylinositol.